Okay, so we're going to pick up where we left off with combination circuits, and I'm going to go over the next couple problems with you. And B is a little bit different. It's probably harder to think about which ones are in parallel and which ones are in series. But remember, the key is always to follow the current and see if the current splits. So locate your battery. We have the total current coming out here, all right? And then it hits a junction point. So we have a split of current at this junction. So that would mean that these resistors are in parallel, okay? Up on the top branch, we have two resistors, and if you follow the current between them, okay, if you look at the current flowing, there's no split between those two resistors. So I would say those resistors are in series with one another, the 50 and the 30. And so those would add directly. And then if you combine those to an 80 ohm resistor, okay, so like think about what that would look like. So we combine those two, they add directly. Now you could see that we have these two resistors. Those are in parallel with one another, and they have to be added. Okay, so those two up top turn into an 80 ohm resistor. This is still a 90 ohm resistor, and we still have this 20 ohm resistor here on the bottom. Okay, so follow the current around still, and you see that the current recollects over the resistors, and then the total current flows over the 20 ohm resistor. Now this 20 ohm resistor is actually in series with the circuit and with the battery because there's no split of the current between that resistor and the battery. So we have a couple that are in series, we have a couple that are in parallel. So we have to add them together like that. So first we start at the top, we combine them over to 80, and then we combine the 80 and the 90 inversely because we have to get their equivalent resistance. So we're going to do R80 inverse plus R90 inverse, and you take the inverse of that, okay? REQ equals 80 ohms, negative 1, plus 90 ohms, negative 1, all to the negative 1. Okay, I have to do that on my calculator because none of you are here to do the math for me. Okay, and those two come out to 42.35 ohms together, right? Which, you know, if you squish them together, that's what one resistor would be, but we would still have that 20 on the bottom row. Okay, so we would have the 42.35 ohm, and then we would have the 20 ohm on the bottom. Now these, if you follow the current around this little, you know, circuit that we've combined, this is now an entire series circuit. So then you would just add up that 42.35 ohm plus 20 ohm, and this actually gives you the equivalent resistance for the entire circuit. So we would get 62.35 ohms, which is important information to note. Okay, 62.35. We would note that at the battery. All right, once you have all this work done, now we can start breaking down our circuit and solving for all of the voltage drops and all of the currents as they split. All right, so now I'm going to do a separate calculation for the total current going to the circuit. So I would use the total potential provided at the battery and the equivalent resistance of the entire combination circuit. So that would be 12 volts divided by 62.35 ohms. And I'm going to round this number a bit so the numbers are a little easier to work with, but you get 0.19 amps. So that's my I total going to my circuit. And if you follow the current around, once again, like you'll see, obviously it splits at this junction, it recollects over here, but we have I total flowing over the 20 ohm resistor, okay? So I could find the voltage drop over the 20 ohm resistor by doing I total times the 20 ohm resistor. So we have the I total is 0.19 amps times Okay, so my app stopped working after 5 minutes, so I need to kind of redo some things. And looking at what we have, this is where the video cut out, so you might see a weird trim in between, and we'll figure it out. So I was looking at the voltage drop across the 20 ohm resistor, and so we have to take the current, which is 0.19 amps, because the entire current is flowing over that 20 ohm resistor, multiply it by its resistance, and you get 3.8 volts. Okay, to find the voltage that goes to the other parts of the circuit, you're going to take the total voltage and subtract from that total voltage the voltage that is supplied to and used up by that 20 ohm resistor. So basically we're going to do 12 volts minus 3.8 volts, and you get 8.2 volts. And if you go back to our picture, and it's already written here because I already did it and it didn't record. So if you go back to our picture, 3.8 volts is being used up by the 20 ohm resistor, and we look at our combined picture over here, and we treat this as a parallel. You know, parallel voltage is constant, so there's going to be 8.2 here and 8.2 here. Now that we know both the voltage and resistance for each part of that circuit, we can now look at the current that's going to the 90 ohm resistor. So that's going to be V of the 90 over R of the 90. So that's going to be the 8.2 over the 90 ohm resistance. Okay. And I'm going to, truncate these numbers a little bit, and it will cause rounding errors at the end, but it's just easier than me carrying 4 or 5 decimals to get the exact numbers. So now we have 0.09 amps breaking at this junction point. Okay, if you look what's coming in, we have 0.19 coming in, we have 0.09 splitting off going to the 90. That would leave us with 0.1 going to the rest of the circuit, so that series branch up top. And you should know series is sick, so current is constant, so we'd have the same current over the 50, we'd have the same current going over the 30. We just do a little Kirchhoff subtraction and realize it's 0.1 amps. Okay, and then we want to go back to find the voltage drop over those resistors. We're really only interested in the 50 because that's what the question asks us for, but we'd have to do the current that goes to the 50 times the resistance of the 50. So 0.1 amps times 50 ohms. Okay, so V for the 50, and remember this is a rounded number. If you use the unrounded numbers, the numbers come out better. Okay, we're going to get 5 volts. You could repeat the same process even though we're not interested in the 30, because the question only asks for the starred resistor. But if you repeat the process with the constant current for the 30 ohm, you're going to get 3 volts, and you'll see that those numbers are missing 0.2 volts, but if you don't use the rounded numbers, you'll get the correct answers. Okay, so I hope this video helps you. I'm going to pause the video and try the next problem in just a minute, if I can. Okay, so third time's a charm. I'm going to start recording letter C. And this one's a little bit more complex. Always start at the most complicated part of your circuit. And if you ever question whether or not the current or whether the resistors are in series or parallel, check if the current splits between them. And for me, looking at this, the most complicated portion of the circuit would be there. And once I combine that, I could start breaking down the rest of the circuit and making it simpler and simpler. So let's start with the 10 and the 5 ohm. Those are definitely in parallel. You could see the junction points where the current's splitting. So those are 2 parallel resistors. So I'm going to combine them together. And then I still have that 4 ohm that's over there. And I have the 3 ohm that's across from it. And don't forget about this 3 ohm that's kind of hanging out by itself. I'm not going to draw the rest of the battery. It's just easier this way. So we have the 3 ohm by itself. We have this 3 ohm, 4 ohm, and then we have to calculate this to combine. So those are in parallel. So REQ is going to be the 10 ohm resistor. So I need to do this kind of nicely. 10 ohm plus 5 ohms, okay, both inverses, and then I'm going to add that and do the inverse of that. So then that comes out to 3.33 repeating ohms, okay? So 3.33 ohms over here. So once again, we're going to follow the current. So the total current comes over here, splits. So if you follow this current across, the 3 and the 4 are actually in series with one another. So, the 3.33. So we can add them directly and combine them into one resistor. So that would be 7.33 ohms up top, still the 3 over here, and the 3 over here. Okay, now still follow the current. We have total current coming in here, splitting up top, splitting to the bottom branch. The 7.33 and the 3 are in parallel to one another. So we need to combine those before we combine them with the outside resistor. Okay, so we're going to do REQ for just those two. 7.33 ohms to the negative 1 plus 3 ohms to the negative 1. Take the whole thing to the negative 1. Okay, so calculator time. All right, 2.13 if I round it. 2.13 ohms. All right, so now I look over here. I have 3 ohms, 2.13 ohms. I can combine them together to 5.13 ohms for the whole circuit, right? So that's my REQ, which I can list at the battery for the entire circuit, right? And knowing that, now that I have all the total information at the battery, I could do a current calculation. So I total equals 12 volts divided by 5.13 ohms. All right, so we're going to get a rounded number, 2.34 amps. Okay, so that's the whole current serving my circuit. We follow conventional current out of the positive side, goes over the 3 ohm resistor. So I'm going to use that information to find the voltage drop over the 3 ohm resistor so I can figure out how much voltage is serving the rest of my circuit. All right, so looking over here, I'll do it in this corner. This is going to be the 3 ohm resistor that is in series with the battery. So that receives the total current, and we're going to use 2.34 times 3 ohms. It's 7.02. So just this little resistor alone uses up quite a bit of the available voltage. Okay, and we can figure out how much voltage is serving the rest of the circuit by subtracting from the total voltage located at the battery. Okay, and sometimes I use my little side diagrams to kind of help me understand what is being used up already, where I have my information listed. So 4.98 volts. Okay, now look at what I'm doing here. Like, I know I have 4.98 volts because I subtracted 12. I took the total voltage, I subtracted the voltage over that initial 3 ohm resistor, and I got 4.98 volts left. Now, if I go up a level from my most, simple diagrams to the more complex ones, these two resistors, these are in parallel. Parallel PVC voltage is constant. So if I know I had 4.98 over this combined resistor, Well, that's still the same voltage supplied over these two parts. So I'm going to have 4.98 over that 3 ohm, and then 4.98 to that top branch. So it's not going to be super simple like that all the time, but you can start to see how these things kind of unfold. Now that I know on that bottom branch over here where we have that 3 ohm resistor, same one over here, now that I know the voltage and the resistance, I could calculate, and I'll do it in another color so we don't get confused with the other 3 ohm resistor, but I could calculate the current going to that branch by doing the voltage over that 3 divided by the resistance of that 3. And we have 4.98 volts divided by 3 ohms, and we get 1.66 amps going to that branch. Okay, so keep that in mind, 1.66. And if you follow Kirchhoff over here, we have total current of 2.34 going to this junction point. Some of it branches to the top, and 1.66 branches to the bottom. So by subtraction, I can figure out how much current is serving that top branch. Okay, so I'll write it here on this diagram, 1.66 amps. I know that we had that total current of 2.34 amps going into there, so 2.34 minus 1.66. We have 0.68 amps serving that top branch. So 0.68, you could go to the next diagram to where they were in series, realize this is 0.68. This is 0.68. Okay, we could find the voltage drop over the 4 ohm resistor. Okay, we just found the current going over the 4 ohm resistor. Okay, so, and if you go back to this diagram, yes, the current splits over here over the 10 and the 5, and then it comes back together over here. So the current going to the 4 is that rejoin 0.68 amps. So we're already like halfway done with what we need to do with the 4 ohm resistor. So we could say 0.68 amps for the 4. Now the only thing left is the voltage drop over that 4. So we're going to do voltage for 4 equals I for the 4 times R for the 4. Okay, so we have 0.68 amps times 4 ohms, and you're going to get 2.72 volts for the 4 ohm resistor. And if you want more practice, you could go through and, solve for the voltage for the 10 and the 5. You could even solve for their individual currents. But to complete this problem, it's not really necessary. Okay? All right, hopefully that was clear for you. Okay? Okay, so this is the last combination circuit in our packet. And this one everyone always has a hard time with. You should follow the current around, and anytime you hit a junction point, okay, realize that that's parallel now. But this is the one people always get wrong because they look at the 7 and the 7 over here, and they see that they are indeed oriented parallel to one another, but that's not the type of parallel we're talking about. We're looking if the current splits between them. And if you follow that around, there was no current split between the 7 and the 7 over here. So these two are actually in series with one another. Okay, this 7 with the star is oriented parallel, and then the 7 over here and the 1.5, if you follow the current, they're actually both in series with the battery. Okay, so we have to do this kind of starting from the right end and work our way towards the battery, because we can't start off with the 2 by the battery and work our way from left to right, right? So let's start off with the 2 that are in series over here, right? So 7 and 7, that would give us 14. So we have the 7 on top. We would still have this 7 over here. We would still have the 1.5 down here. And then those 2 would combine. It doesn't really matter how you draw it or where you draw it, but it would be a 14 ohm over here. So we have a 7, we have a 1.5, and we have a 7 over here. Okay, so now the 7 and the 14, those are definitely in parallel with one another. So I'm going to combine those next. The 2 that are in series with the battery would still be there. So we have inverse 7 plus inverse of 14, take the inverse of that. So that would be 4.66 ohms by doing the inverse of those 2. And then we still have the 7, we still have the 1.5. Now all of these are in series with the battery, so we could just add up for the REQ. We could add up the 7 plus the 1.5 plus 4.6, and I'm going to round that to, actually I'm going to round this to 7 because it's actually 4.66. Okay, so I have 13.17 ohms for the REQ for the entire circuit. Okay, I didn't show a lot of work there because hopefully you're getting the hang of this by now. All right, so I have the REQ, I have the total voltage. So now I'm going to do the total current for the circuit. So V total over REQ. We have our 12 volts. We have 13.17 ohms. So we're going to do 12 divided by answer. We have 0.91, I guess, I don't know, 911. You can reduce that to 2. It's just going to make more rounding errors. All right, so now that we know the current, that's going to be the total current over this one, the total current over this one. You could work, you could actually work on any of these pictures. Just realize what's going on and where the information applies. So if we're to the simplest series circuit part, you know that it's constant current throughout. It would be the total current going through each one. So we could find the voltage drop across all of these resistors. Okay, so we could actually do that now if you wanted to. So let's work on getting the voltage drop across each of these resistors by doing V equals IR. You could do it twice, you could do it 3 times, you could whatever you want to do, or you could subtract from the total voltage. So I'm going to use each one of those variables shown. Nope, things are opening up that I don't want to open up. Okay, so we're going to continue calculating the voltage drop over these 3 resistors. So we're going to do V equals IR using the 2 givens next to each one of these variables. So bear with me while I do out some math. So this one's going to have a voltage drop of 6.377 volts, followed by, this one's going to be definitely some rounding error over here. We're going to have 4.25, we'll leave it at 3 decimals, 4 amps, and then 0.911 times 1.5 over here. It's voltage drop of 1.367 volts. Why am I writing amps? Boop. Volts. Okay. Right, so if you look back at our other pictures, and applying the knowledge that we have, this would still be 1.367, gosh, I can't stop writing, amps. Volts with 6.377 volts over here. And then this end one that we combine to that one in series, now this is a parallel branch, so parallel PVC, we would still have 4.254 volts here, 4.254 volts here, okay? And to complete the problem, we just want the voltage and the current over that 7 ohm resistor right in the middle. And if you look over here, we already have the voltage, we have the resistance. So we only have one more calculation to do, and that's for that middle 7 ohm resistor. So we're going to do V equals IR, 4.254 volts divided by 7 ohms. And we should get 0.60, we'll round it to 8 amps over that resistor. Okay, and you can do additional work to figure out, well, how much current is going to this one. You can either do subtraction or you can do another Ohm's law to figure that out. But it all should work out either way. I just did a quick little calculation over here, and this came out to 0.304 amps, and this one, remember, was 0.06 or 0.608 amps. So if you add those two together, if I could type in the numbers correctly, it actually comes out to 0.911, which is what we had supplied at the battery. So everything works out. So our final answer for current is over here. Our final answer for voltage, I'll just write it nice and big so you can see it. And hopefully these combination circuits are getting a little bit easier for you. Okay? Next stop is going to be Kirchhoff's second rule.